Hello everyone, welcome to our video on weak acid equilibria. In this video, we will learn how to write ionization reactions for acids using the Bronsted-Lowry theory of acids and bases. We will define weak acid equilibria, and we will learn how to write the equilibrium expressions for weak acids, which are referred to as Ka expressions. Recall that we differentiate between strong and weak acids by the extent at which they ionize in water. Weak acids are acids which ionize incompletely. Typically we say less than 50%, but we will see that more often than not, it's much less than that. Recall as well that the Bronsted-Lowry theory of acids and bases defines them in terms of pairs. We cannot have a Bronsted-Lowry acid without the presence of a Bronsted-Lowry base, a proton acceptor. Previously, you've learned how to write the ionization equation for acids. On the left side of the ionization equation, we have the unionized acid in its molecular form in the case of HCl. On the right-hand side, we write the ionized acid, which, in the case of an acid, loses one of its protons, and then the other species is the anion, or the rest of the molecule. In this case, it's a 1:1:1 ratio, and because it's a strong acid, it reacts stoichiometrically, or completely. In order to write this ionization equation from the Bronsted-Lowry theory perspective, we need to pair that acid with a Bronsted-Lowry base. If the acid is going to donate a proton, we need a species that can accept the proton. In this case, the other species will be water. Because we are dissolving the HCl in water as the solvent, some of those water molecules are now going to be active participants in the acid ionization. In this case, water is acting as the proton acceptor. The hydrochloric acid donates its hydrogen ion to the water molecule, and that forms the hydronium ion. The hydronium ion is the conjugate acid of the water molecule. The chloride ion, Cl1-, is the conjugate base of the hydrochloric acid molecule. These two equations are equivalent. Even though water shows up in the second equation, we can see that for every one HCl molecule, we generate one hydrogen ion or one hydronium ion. It's still a 1:1 ratio. We are just explicitly showing one water molecule involved in the reaction. Strong acid ionization only occurs in one direction. It is a complete reaction and is not reversible. As such, we will often use the Arrhenius theory to show the ionization of strong acids, and we'll see as for strong bases as well, because it accounts sufficiently for the properties of these acids and bases. There's not really often a need to use a more complex theory if a simpler theory will suffice in terms of explaining the phenomena that we observe. Weak acid ionization is a different story. Let's use the example of acetic acid, CH3COOH. We will see this acid used many times when talking about acid-base equilibria. So just a reminder that acetic acid, even though it contains 4 hydrogens, is a monoprotic acid. That's why one of the hydrogens is written separately from the other 3, because when it ionizes in water, it only loses one of those hydrogens. We see that the acid ionization equation looks exactly the same to that of the strong acid HCl. Acetic acid, the unionized molecule, donates a proton to the water molecule. So acetic acid is the Bronsted-Lowry acid, the proton donor. Water is acting as a Bronsted-Lowry base, the proton acceptor. By accepting the proton, that produces the hydronium ion, H3O 1+, and that's now a conjugate acid, and the CH3COO1-, the acetate ion, is the conjugate base. But what we have now is the case where the right side of the equation has an acid-base pair that can cause the reverse reaction to occur. The acetate ion can readily accept a proton. It is a good base. And the hydronium ion can readily donate a proton, so the reverse reaction can occur. We know by definition that weak acids ionize incompletely, so this reaction never goes completely to the right-hand side. As a result, we now have the conditions for an equilibrium system, a reversible reaction that can occur in a closed system, and that occurs incompletely. In general, we can express the ionization reaction for any weak acid, which we'll just call HA. H would be the proton that's being donated. A would be the rest of the molecule, whatever it is, as this equation here. The left-hand side consists of the unionized acid and water. The right-hand side consists of the hydronium ion and the conjugate base or the anion related to that acid. As with all equilibrium systems, they will obey the equilibrium law, so we can write an equilibrium law expression. This is the general form for all weak acid equilibrium expressions. Even weak acids, which are polyprotic, which donate more than one hydrogen ion, we will always consider their ionizations one hydrogen at a time, which means rather than having a 1:2 ratio in terms of the acid to the hydronium ions produced, we can always look at it in a 1:1:1:1 ratio. This simplifies a lot of things for us because our equilibrium expressions will always look generally the same. The only thing that's going to differ is the identity of the rest of that molecule, that A and the conjugate base A1-. As with many equilibrium law constants, we give this a specific subscript referring to the reaction that it is referencing. In this case, we call the acid ionization constant Ka. We've already looked at heterogeneous equilibrium when we've considered solubility equilibrium, and we know that water, being a pure substance and as the solvent, is required in the equilibrium system, but is not part of the equilibrium law expression. It's always important to think about what the value of that Ka means, not mathematically necessarily, but in terms of this real physical system. In this case, the size or the magnitude of that Ka value is going to tell us about the extent at which that weak acid ionizes. The larger the Ka value, as it gets larger and larger than 1, is going to mean that that weak acid produces a higher concentration of hydronium ions, which means it ionizes more. The smaller the Ka value, values of greater than 0 but less than 1, so we get very, very small values, those acids ionize very incompletely and only produce a very small concentration of hydronium ions. This concludes our introduction to weak acid equilibria. Our next steps will be to learn how to solve some common mathematical problems using this equilibrium law expression.